Hi to all my Braineries. The Brainery channel is back with another video on a topic Coulombs Law. Here in this video, I will be teaching you about the concept and the derivatives related to Coulombs Law and all the numericals concerned this Coulombs Law I will be teaching in the coming video. So let's start with the concepts of Coulombs Law. Coulombs Law helps us to find the force between the 2-point charges. Now, what the key point here is that it always exists between the force exists between the 2-point charges. The name of the point charges I have explained earlier in my previous video. The concept of point charges, you may refer to that video. So here, now if we have two charges, that is one is Q1 and the other one is Q2 in a space or in vacuum, and they are separated by a distance r, then the force exists, that is a force of repulsion exists between these two like charges, and whose magnitude the Coulomb's law will help us to find it out. It states that the force is inversely proportional to the square of distance between these charges. It is directly proportional to the product of magnitude of the two charges, and it acts along the line joining the two charges. Now here, this statement is very important, that it always acts along the line joining the two charges. That means it always acts along this line. It never acts along this line. If we draw on this line, no, it is not. If we withdraw this particular line, no, again it is on this direction, it will not be acting. There is only one particular direction in which the Coulomb's force law will be acting. On combining these two factors, what we will get? F equals to K Q1 Q2 by R square. Where this? Because we have removed the proportionality sign, so we have to introduce one constant of proportionality, which is K. Now the value of the K is 1 upon 4 pi epsilon naught. So the formula for F becomes 1 upon 4 pi epsilon naught Q1 Q2 by R square. Now we will be learning more about this constant of proportionality, that is 1 upon 4 pi epsilon naught. In SI unit, the SI unit of K is equals to 9 into 10 to the power 9 Newton meter square per Coulomb square. Now, here one symbol we are finding epsilon naught. This epsilon naught signifies the permittivity of a medium. Now, this is a new word. Throughout the unit 1, we will be referring to epsilon naught, epsilon, epsilon r. All these are the permittivities. So, let us first begin with the introduction of this word, that is permittivity. Permittivity is the property of the medium which determines the electric force between two charges situated in the medium. Minded, it is that property which determines whether the force between the two charges is going to be the very strong or very weak. That is called as the permittivity. So, if the charges are present in a medium, the force between them is going to be a weaker one, or it could be a stronger one. That is the deciding factor, is called as the permittivity. Now, I hope the meaning of this epsilon naught might be clear to you. If the charges are present in any other medium, then we have the epsilon. So, the force between the two charges may vary. It depends on medium to medium. The SI unit of epsilon is this much Coulomb square per Newton per meter square. See here, the unit of epsilon naught and the unit of K, they are reciprocal to each other. So, it is very easy to remember these units. So, please remember the values and the units, as that can be asked in the exams. Its dimensional formula is this one. This can also be asked as a 1-mark question. So, please go for it. Now, next, another very important thing in CGS system. CGS means centimeter unit system. The value of K becomes 1. So, in CGS, the formula for the Coulomb's force becomes Q1 Q2 by R square. There is no constant of proportionality because its value is going to be 1. So, all the important concepts related to Coulomb's law I have explained you. You will write all these concepts. You are going to get full marks in the exam. Don't miss to write all the statements. Next, the topic is unit of charge. In the previous video, I have explained about the electric charges in detail. So, there what we have learnt is that as a unit of charge is Coulomb. Now, in this video, we will define the Coulomb. What is 1 Coulomb of charge? So, for that, in the equation, basic equation, what we have, F equals to 1 upon 4 pi epsilon naught Q1 Q2 by R square. In this equation, if we are going to put the value of charges Q1 Q2 as 1 Coulomb and the distance as 1 meter, so this particular term is going to become equals to the 1. So, what we are left with is F equals to 1 upon 4 pi epsilon naught 9 into 10 to the power 9 Newton. So, this is a constant value for the force when the two charges are of magnitude 1 Coulomb and are separated by a distance of 1 meter. So, based on this statement, we can have the definition of 1 Coulomb is, it is that amount of charge which repels an equal and similar charge with the force of 10 to the power 9 Newton when placed in vacuum at a distance of 1 meter from it. Mind it, here, there are certain keywords. What are they? The charges must be present in vacuum. They must be at a distance of 1 meter. the magnitude of charge should be the 1 coulomb. So there will be a force of attraction and repulsion between them of magnitude 9 into 10 to the power 9 Newton. So if you can give this particular definition. Now in CGS, the unit of charge is ESU, that is called as electrostatic unit, or it is called as the stat coulomb. Now based on this, we can again define the one ESU of a charge. It is that charge which repels an identical charge in vacuum at a distance of 1 centimeter from it with a force of 1 dyne. So in this definition, these two are the keywords. There you have to just change the unit of the parameters. What are they? The two charges must be at a distance of held at a distance of 1 centimeter, and the force between them will become 1 dyne. Then the magnitude of the charge is equals to the 1 coulomb, where 1 coulomb is equals to 3 into 10 to the power 9 stat coulomb. This is the relation between SI and CGS system of unit. So please go for it. This is again another important key point or a concept related to the Coulombs law. Next, we have the Coulombs law in vector form. Now, in vector form, we know that vector is a quantity which is having both magnitude and direction. So, when we are dealing with force, so the direction of force is important. So, in this article, we will be concentrating on the direction of force. Whenever we have the two charges, suppose Q1 and plus Q2, so there the force acting on these two charges will be what? So where various terms that we will be having is F21 and R21. What is F21? F21 is the force on this second charge because of the presence of first charge. Now this first charge will be repelling this Q2, so the direction of this F21 will be in this direction. And R12, what is R12? R12 is the unit vector pointing from Q1 to Q2. If we start moving from Q1 towards Q2, what we will find that we are moving in a direction of R12 position vector. That means the direction of F21 and the direction of F12 are same. So we can have the formula for F21 as 1 upon 4 pi epsilon naught Q1 Q2 by R square. Minded, here this is the magnitude part only. Now since we are dealing in a vector form, so if this side is having a particular direction with the direction of F21, in that direction we are having a position unit vector, that is R12. Here this R12 and F21, they are pointing in the same direction. So this is our balanced equation in the vector form, where R12, that is unit vector, can be represented as vector R upon its magnitude. Next we have F12. What is F12? It is the force on first charge due to second charge. Mind it, here this is the first charge and this is the second charge. They are of similar nature, so naturally they will start repelling. So this is the direction of F12 in this direction, F12, and in this direction what is the position vector? The position vector is that when we are moving from Q2 towards Q1, that is, it is having the direction of R21, which is the unit vector pointing from Q2 to Q1. So what our formula will become? Formula for F12 will become this magnitude part and to R21. So here F12 and R21, they are pointing in the same direction. So this is the formula, and one basic formula we have for F21. Now in the diagram, what we are finding is that the position vector R12 and position vector R21, they are opposite to each other. So we can write unit vector R12 is negative of R21. So now here in this formula of F12, if I replace this R21 with minus of R12. See here minus, because here I am replacing R21 with the sign of minus of R12. Now here what we are having R12, that means it becomes the formula for F21. So F12 is nothing but it is equals to negative of F21, that is force on second due to the first charge. This is how we have derived the Coulombs law in vector form. I have given all the necessary steps to write this particular derivation, so please go for it. And the important consequence of this Coulombs law in vector form is that Coulombs law obeys Newton's third law. This particular statement says that for every force there is equal and opposite force. So it confirms the Newton's third law. That means Coulombs law in vector form obey the Newton's third law. An important part, F12, that is force on 1, is plus the force on second charge must be equal to 0. Sum of the forces in a particular system will always be the 0. So here these are all the necessary steps for the derivation of Coulombs law in vector form. In exam, if you will write, you are going to get the full marks. Next we have the concept check. Now let us see. The general question that can be asked in the exam is general question, the repulsive Coulombian force. That is, it is for Q1 is Q2 is always greater than 0. How we can represent this repulsive Coulombian force? If we have the two like charges, that is two negative charges. This one is the negative charge and this one is also a negative charge. So this is the direction where the repulsive forces will be present. So Similarly, we have another like charges, that is two positive charges. So repulsive Coulombian forces will always point opposite to each other. This is how, and Q1, Q2, the product of Q1, Q2 will always be greater than 0. Here see, if we have two minus negative charges, here see, if we have two negative charges, this negative charges, and here this negative charges, negative into negative will become again positive, that is it will be greater than 0. And if we have two positive charges, two positive, product of positive charges will become greater than 0. So if this situation is asked, what is the significance of Q1, Q2 is greater than 0, that means we are having the system of two like charges. This is the one concept. Next, we have attractive Coulombian forces. For that, Q1, Q2 must be less than 0. Now, attractive Coulombian force means the force must be attractive in nature. Now, when this force will be attractive in nature? When we have the two unlike charges. That is, if one is negative charge and the other one is positive charge. So, here what we are finding, the Coulombian forces pointing towards each other, that is, this is attractive in nature. So whenever it is asked if Q1, Q2 is less than 0, that means it signifies that one of the charge we are dealing is negative and the other charge has to be the positive. Then only this product will give us the attractive Coulombian force. So this is an important concept check related to the Coulomb's law. When the Coulomb's force are repulsive, so with which type of the charges we are dealing, and when the Coulombian force is attractive, with which type of the charges we are dealing. So please keep this in mind. Next is limitations of Coulomb's law. So all the important derivations related to Coulomb's law we have learned. Now there is one limitations. You might be reasoning that it is valid in all situations, but it is not at all. It is valid only under the following condition. Let us see. Whenever the electric charges must be at rest. So this is again a keyword. When the charges are at, then only the Coulomb force exists between these two charges. When the same charges are in motion, then this force, this law is not at all valid. Next is the electric charge must be the point charges. Again here the term point charges is coming, whose meaning is that the dimension of charges must be much smaller than the separation between them. So that is why the Coulomb's law is valid only in case of the point charges. Next we have the separation between the charges must be greater than the nuclear size. That means within the dimensions of nuclear size, this Coulomb's law has no application, because there the nuclear forces dominates over the Coulombian forces. So these are the three cases, three conditions under which the Coulomb's law is valid. Now next is dielectric constant or relative permittivity, another very important topic. Now see, first of all, what is permittivity? So permittivity is the property of a medium which determines the electric force between two charges situated in that medium. In the previous article, we have learnt that whenever two charges are placed, there is a force between them. But now here, we will be concerning about the medium in which these two charges are being placed. So what is the role of the medium? With the help of an example, we can find is that the force between two charges located some distance apart in water is about 1/80th of the force between them when they are separated by the same distance in air. What does this statement mean is that, suppose if we are having the two charges Q1 and Q2 that are present in air separated by a certain distance, so naturally a magnitude F, force of F will be present in between these two charges. But when the same two charges are present in a medium, let us suppose the medium becomes water, the magnitude of charges are same, the separation between them is again be the same, everything is same, only the thing is that we have changed the medium, which is water. So now whatever the force is acting between them in water will be 1/80th time that the force which was present earlier between them when they were in air. That means the force is reduced. That means whenever the charges are placed in a medium, the force will be reduced. Now here what I am referring is certain table, a relative permittivity of certain mediums. The first medium is vacuum, whose value is 1. Air we have 1.00054 and in water we have 80. So see here, the medium which is having that much greater electric constant, that much force will be reduced by that much. That is more the relative permittivity, lesser will be the force. That means these two charges will be interacting with the very lesser magnitude in a medium, whereas in air they are interacting with the greatest magnitude. That is what is the concept of relative permittivity is all about. So why the force in the medium is reduced? The force in a medium is reduced because the absolute permittivity of water is about 80 times greater than the absolute permittivity of free space. Here you can find is that the permittivity of water is 80 times that in the vacuum. So more is the relative permittivity, the lesser will be the force present between them. Lesser is the permittivity, more or the strong force will be present between the two charges. This is the concept of the permittivity. So directly, in indirect sense, it gives us the magnitude of the force, how the force is going to be affected when the charges are present in different media. Now, let us find one formula related to this. Whenever the force is present between the two charges in vacuum, we are having a formula F vacuum is equals to 1 upon 4 pi epsilon naught. Here we are dealing with pi epsilon naught and Q1 Q2 by R square. But when the same charges are present in any medium, what the formula will be? F medium. See here, we have to write F medium, which becomes 1 upon 4 pi epsilon. Here the difference is that we are not writing epsilon naught, because epsilon naught is the permittivity of a free space or a vacuum, whereas epsilon is called as the permittivity of the intervening medium. It is called as the permittivity. Yani ki this epsilon is the deciding factor which will decide what will be the magnitude of the force between the same two charges which were there in a vacuum. So what is the effect of this medium? If we will divide these two forces, that is force in vacuum and force in medium, the ratio of these two forces, we will get the ratio of epsilon upon epsilon naught, and this ratio is called as the relative permittivity, which is equals to epsilon upon epsilon naught. So this is also equals to ratio of F vacuum to the F medium. So the definition of relative permittivity, it is the ratio of force between two charges placed some distance apart in free space, ratio of force in free space to the force between the same 2 point charges when they are placed same distance apart in a given medium. So it is the ratio of two forces. So another important concept related to this relative permittivity is that it is a dimensionless and a unitless quantity. Keep in mind, for epsilon naught we have defined the unit in the previous article. In this video only I have given you the unit and the value of epsilon naught, but here for the relative permittivity it is unitless and a dimensionless quantity. It will be having only a magnitude part. So the important concept always what you will find whenever the same two charges are placed in a medium or whether they are placed in a vacuum, the force present between them in a medium will always be less than the force between the same two charges when they are present in the vacuum. That means in vacuum the charges experience the greatest amount of force, and in any other medium the magnitude of the force always decreases.